Okay, so the standard normal distribution. The normal, it is a normal continuous distribution, and it is the most important of all of them. And the graph is it has a shape that we call a bell shape. If you've ever heard of the bell curve or bell-shaped curve, that's where they're getting it from. It's a curve that a lot of professors will do in college. You see this information across a whole bunch of disciplines. And so that's why it's actually really important whenever you take statistics for those classes, a lot of times this is a very large portion of that class. So we're going to be talking about the normal distribution, the standard normal distribution, they're slightly different, and the applications associated with them. So it has two parameters, so two pieces of information, numerical information that you need to know. It's called, and they are the mean, which is mu, and the standard deviation, which is sigma. So if x is a quantity to be measured, and it has a normal distribution with those means and standard deviations, we can write it in this notation. This is for you to know that if I write x with that little squiggly and I have a capital N, that tells you it's a normal distribution, and the information inside the parentheses, the first thing is the mean and the second thing is the standard deviation. So you need to be able to go between the information and between that notation. You need to be able to understand what they mean, okay?
What do x and n mean?
Okay, so the properties of any normal distribution, the graph is symmetric and it is bell-shaped. The normal curve is symmetric about the mean. So that dotted line that goes straight down the center and cuts it in half is your mean. And what that means is that half of the data is to the left and half of the data is to the right, which should make sense. The mean, median, and mode are all centered in the middle. So if I give you a normal distribution and I tell you the mean, you automatically know the median and the mode as well. And just like what we talked about in 5.1, the total area under the curve is 1.
So this is kind of applying.
So a change in the standard deviation causes a change in the shape of the curve. It can become fatter or skinnier depending on whatever sigma is. So right there, I give you 3 examples. The one in the middle, the blue one, that is your standard deviation is 1 and a mean of 0. So it's centered along the x-axis if you're looking at it along a graph. For what's in green to the left, it's got a mean of -2 with the standard deviation of 2. And then the one in red to the right, it's got a mean of +2 with a standard deviation of 1/2. The smaller the standard deviation, it kind of tightens up the data. It brings it in. Does that make sense? If it's got a larger standard deviation, it spreads it out further because it means it's spread out more. Does
it deviate from the mean?
That's how far it deviates from the mean, yes. The standard normal distribution is a normal distribution of standardized values called z-scores. So whenever we were talking about z-scores, those kind of come into play here. A z-score is measured in units of the standard deviation. The z-score tells you how many standard deviations the value is above or below the value of mean. Remember, positive means it's to the right, negative means it's to the left. So for example, the mean of a normal distribution is 100. The standard deviation is 50. How far away is the value of 200? How many standard deviations? The standard deviation is 50 and the mean is 100. It is 2 sets of 50 away, so it is 2 standard deviations away from the mean. Does that make sense? The mean mu for the standard normal is 0, and the standard deviation is 2. So when you find the z-scores, you get mu is 0 and sigma is 1. So the z-scores take whatever the normal distribution is and turns it into a standard normal distribution. And just like when we learn z-scores, it helps you take multiple sets of data and compare that, have a relative way to compare them. So you're taking apples, oranges, and bananas and being able to compare all of them as one thing because you're turning them into the same thing using z-scores. Okay, so there's our formula for z-score, which we've seen before. So if you have any normal distribution, like on the left, it will take it and it will turn it into your standard normal. So that way you can compare it, okay? The transform and the reasoning why we do this is because if you flip to the very back page of your notes that I gave you, you're going to see this table of values that we are going to be using quite a bit, okay? For the tests and the quizzes, you have one that I will be giving you, okay? And we're going to talk about how to use that before you need to know. But the purpose of the standardized normal is you have to be able to know how to use this table, but this table's values only apply to the standard normal. So if I give you anything but the standard, you have to turn it into the standard to be able to use this table. Does that make sense? Yeah? Okay. All right, the transformation z equals x minus mu over sigma produces the distribution. Z is the normal with, again, 0 is the mean, 1 is standard deviation. That's what this notation means. The value x in the given equation comes from a normal distribution with mean mu and standard deviation sigma. So suppose x is normal with a mu of 5 and a sigma of 2. So that's what this right here means. So my mean is 5 and my standard deviation is 2. So suppose x equals 9. So find the z-score. So remember we do, using this formula, 9 minus mu over sigma.
2.
And you're going to get z is 2. That's correct. This means x equals 9 is 2 standard deviations, or 2 times sigma, above or to the right of the mean of 5. Now, you probably could have looked at that without using the z-score to determine that 9 is 2 standard deviations, but when we start talking about the decimals, that's where you need to be able to turn it into a z-score. Okay? Now, suppose x equals 1, find the z-score associated with it. So go ahead and you do that.
Is it the same mu?
All right. So in a normal distribution, x equals 5 and z equals negative 1.25. This tells you that x equals 5 is 1.25 standard deviations to the left of the mean, right?
I don't know
Correct?
if it's up or down.
Is there a
All right, how about the next one? In a normal distribution, x equals 3, z equals 0.67. What does that tell you?
0.67.
It is 0.67 standard deviations to the what?
Right.
To the right. Good.
So we can bring this math compass?
All right, properties of the standard normal. The graph is symmetric and bell-shaped. The mean is 0. Standard deviation is 1. Normal curve is symmetric about the mean. So half the data is to the left, half the data is to the right. the mean, median, mode are all centered, and the total area of the curve is 1. So this is exactly like the standard norm, or just like the normal. It's just that we can tell you specifically what the mean is and what the standard deviation is. We know those values for the standard normal. Okay, so that's just kind of summarizing it. So the mean of a normal distribution, not standard normal, just normal, is C, mu. The mean of a standard normal is 0. The standard deviation of a standard normal
1.
is 1. The mode of a normal distribution is mu. It's the same thing as the mean. The area to the right of mu in a standard normal distribution is what? Nope.
Is it D?
The area.
C. Oh, no, it's 1, right? It's always 1.
No, the whole thing is 1, so to the right of mean is going to be half. Remember, half of that is to the right, half of that is to the left.
Oh, I got you.
And then true or false, another name for the normal distribution is a z-distribution. False, because it's the standard normal.
We had to take these